Hidden deep in the Siberian forests are giant structures capable of seeing thousands of kilometers beyond the horizon. Radar stations as tall as a 20-story building, antennas covering an area the size of 2 football fields, radiation power comparable to that of a power plant. These facilities were built over decades, cost billions, and were then mysteriously destroyed. The Americans demanded their dismantling, then offered to complete their construction. The stations were blown up, burned, and buried under rubble. Legends arose around them about strange phenomena and secret experiments. What is really hidden in the Taiga under the guise of missile defense systems? What secrets are buried under the concrete ruins? Now you will learn the story that they preferred not to tell. If you are interested in the secrets of military technology and secret Cold War facilities, subscribe to the channel and like the video. And in the comments, let's discuss the question: could the most powerful radars have been used not only to detect missiles, but also for secret experiments on the atmosphere and ionosphere? Were the stations part of programs that are still kept secret in the archives? Share your opinion. Deep in the Siberian Taiga, hidden from the eyes of casual travelers and protected by numerous military cordons, stand structures that look as if they were created by representatives of an extraterrestrial civilization. Giant structures made of steel and concrete, reaching the height of multi-story buildings, soar into the sky at a certain angle. These are not sets for a science fiction film or abandoned industrial facilities. They are long-range radar stations capable of seeing what lies beyond the horizon, thousands of kilometers away. Their antennas pick up radio waves reflected from objects that conventional radar would never detect due to the curvature of the Earth. The principle of over-the-horizon radar is based on using the ionosphere as a giant mirror that reflects radio waves back to the Earth's surface. The station emits a powerful pulse in the meter range. The wave goes into the sky, reaches the ionosphere at an altitude of 150 to 1,000 kilometers, and is reflected back, falling to the ground far beyond the horizon. If the reflected wave encounters an object in its path, a rocket, an airplane, a spacecraft, it is reflected again and returns to the station's receiving antenna. Computer systems analyze the signal's transit time, its distortions, and the Doppler frequency shift, and reconstruct the object's trajectory with an accuracy of several kilometers. The system is capable of simultaneously tracking dozens of targets the size of a soccer ball at a distance of up to 6,000 kilometers. Imagine an antenna with an area of 10,000 square meters. This is the size of the receiving part of the daryal station, the main element of the Soviet missile attack warning system. 100 meters long and 100 meters high, it is filled with nearly 4,000 special cross-shaped vibrators, each of which is controlled separately. The transmitting antenna is smaller, 40 by 40 meters, but it contains 1,260 replaceable modules, each of which outputs 300 kilowatts of pulse power. The total radiated power is measured in hundreds of megawatts, comparable to the power of a small power plant. Because of this monstrous energy, the transmitting and receiving positions are separated by a distance of 500 to 1,500 meters. Otherwise, the radiation itself would simply destroy the sensitive receiving equipment. The construction of such a complex required the creation of an entire secret infrastructure in the Taiga. Roads, power lines, military towns, and command posts. Thousands of specialists spent years building these structures in harsh climatic conditions, observing a regime of absolute secrecy. Local residents saw hundreds of trucks carrying equipment into the remote taiga, roads being built where there had previously only been bare trails, and power lines with pylons tens of meters high being erected. Officially, they were told that these were industrial facilities or scientific stations being built. But the scale of the work, the level of secrecy, and the nature of the structures suggested that something related to the country's defense capabilities was being created here. The stations were given code names: Yeniseisk 15, Usolye Sibirskoye 7, Object OS 3, Object OS 1. These designations had no obvious connection to the actual location and served as additional camouflage. Why were these facilities built in the Siberian taiga, far from borders and large cities? The answer lies in the geometry of radar detection and the geopolitics of the Cold War. The stations were supposed to monitor the directions of possible missile attacks, northeast from North America across the pole, southeast from China and Pacific bases. Their location deep within the territory ensured maximum warning time and protection from a possible cruise missile strike. But was there another reason for choosing these locations that was not officially disclosed? The history of the daryal system began in the late 1960s, when Soviet military and scientists realized that existing radar systems were unable to reliably detect new types of ballistic missiles. The advent of intercontinental ballistic missiles with multiple warheads radically changed the requirements for missile attack warning systems. A single such missile could carry 10 or more warheads, each of which was guided to a separate target, plus dozens of false targets. Lightweight inflatable simulators, metal reflectors, and jammers. Instead of a single mark, hundreds appeared on radar screens, and the task of identifying real warheads became extremely difficult. The existing Dnieper stations, which had been in operation since the early 1970s, could no longer cope with the flow of information. Radically new technical solutions were needed. In 1968, a preliminary design was developed for a new radar station capable of detecting and tracking about 100 targets simultaneously at a range of up to 6,000 kilometers. But how could such a system be implemented? In the early 1970s, two leading Soviet research institutes proposed competing projects. The first project was developed by a group of employees of the Radio Engineering Institute of the USSR Academy of Sciences, led by Viktor Mikhailovich Ivantsov. They proposed a revolutionary technology for that time: the use of a phased antenna array with pulsed radiation and electronic beam scanning. This meant abandoning the mechanical rotation of the antenna and switching to beam control by changing the signal phase on individual elements of the array. The second project was presented by specialists from Nyarty, led by Alexander Nikolaevich Musatov. Their concept was based on the proven principles of previous stations in the Duny family, a frequency scanning method with continuous radiation. This approach was more conservative, but it allowed the use of existing production facilities and technologies. Both projects met the military's technical specifications and could deliver the required performance. However, the first option was chosen despite its technical complexity and the need to develop fundamentally new technologies. Why? Because it opened up the possibility of a technological breakthrough in radar technology, creating systems that would be decades ahead of their Western counterparts. Viktor Ivantsov was appointed chief designer of the new radar, with Anatoly Skosirev as his first deputy. Years of work began to turn theoretical concepts into working equipment. Creating a phased array antenna of this scale required the development of thousands of special modules, each of which had to work in sync with the others. The slightest error in phasing could distort the directional pattern and render the station useless. Controlling such a system required a powerful computing complex capable of performing billions of operations per second. A fantastic performance for those times. On April 14, 1975, the Central Committee of the Communist Party of the Soviet Union and the Council of Ministers of the USSR issued a decree on the creation of the daryal radar station in the northern and southern missile-threatened directions. The stations were intended to close gaps in the radar field of the missile attack warning system. The area around the city of Pechora, in the Komi Republic, was chosen for the northern direction, and the area around the city of Kutkashin, in the Azerbaijan SSR, for the southern direction. But that was only the beginning. At the same time, work began on an improved modification of daryal U, which was to receive even more advanced characteristics thanks to a new computing complex based on a multiprocessor computer of the M13 type, with a performance of up to 2.4 billion operations per second. This machine could optimally distribute the emitted energy between space survey and individual target tracking modes, adapt the receiver's operation to interference conditions, and improve range resolution by 2 to 4 times. The minimum detection range was reduced from 150 to 15 to 20 kilometers, which made it possible to see low-flying targets. The creation of such technology in the 1970s was a feat of Soviet science and industry. But few people know that, in parallel with the official program, other research was conducted related to the capabilities of these powerful emitting systems, the results of which remain classified to this day. The technical characteristics of the daryal stations amazed even experienced engineers. The main receiving antenna was an active phased array antenna measuring 100 meters wide and 100 meters high, with an area of 10,000 square meters, comparable to the size of a city block. 3,950 cross vibrators were built into this gigantic structure, each of which served as both a receiver and a control element for the directional pattern. The signal from each vibrator was fed to its own low-noise amplifier, then passed through a phase shifter, and was combined with the signals from the other elements. By changing the phase shift on different elements of the array, the system could instantly direct the beam to any point within the viewing sector without mechanical movement of the antenna. The sector covered 90 degrees in azimuth and 40 degrees in elevation, allowing control of a huge area of space. The transmitting antenna was smaller, measuring 40 by 40 meters, but its energy characteristics were monstrous. There were 1,260 replaceable transmitting modules, each containing a powerful tube transmitter with a pulse power of 300 kilowatts. At the moment of pulse emission, the total power exceeded 370 megawatts, more than the power of many thermal power plants. The energy of such a pulse was sufficient to heat a ton of water to boiling point in 1,000th of a second. The radiation occurred in the meter wave range, which was optimal for reflection from the ionosphere and penetration through atmospheric interference. Separating the transmitting and receiving positions by a distance of 500 to 1,500 meters was a necessary measure. When the transmitting antenna emitted a pulse with a power of hundreds of megawatts, even a microscopic part of this energy reaching the receiver could disable sensitive electronics. Therefore, the receiving position was located on another hill or behind natural folds in the terrain, which provided additional shielding. Kilometers of cables were laid between the positions to synchronize the work and transmit information. The station operated in pulse Doppler mode, emitting a series of short pulses and analyzing not only the return time of the reflected signal, but also the change in its frequency due to the Doppler effect. A ballistic missile travels at a speed of several kilometers per second, which causes a noticeable shift in the frequency of the reflected signal. The magnitude of this shift was used to calculate the radial velocity of the target, its speed toward or away from the station. By comparing the data from several successive pulses, the system reconstructed the trajectory of the missile and could predict the point of impact of the warhead with an accuracy of several kilometers. The station's computing complex included several specialized computers. The main machine, a multiprocessor system called M13, processed radar data, controlled the phased array, tracked targets, and generated information for the warning system. Its performance of up to 2.4 billion operations per second was enormous by the standards of the 1970s and 1980s, comparable to the combined power of thousands of personal computers of that time. The computer cooling system required its own pumping station and cooling towers. The computers generated so much heat that it had to be taken into account in the energy balance of the entire facility. The station's power supply was provided by a special substation with a capacity of tens of megawatts. Laying power lines to remote sites in the Taiga became a separate engineering challenge. Backup diesel generators could keep critical systems running for several days. The station's annual electricity consumption was comparable to that of a small town. Maintaining the complex required the constant presence of hundreds of military personnel and civilian specialists, operators, engineers, antenna system maintenance technicians, programmers, and computer specialists. Entire military towns with residential buildings, schools, kindergartens, and shops were built for them. In the Siberian Taiga, these towns became islands of civilization, connected to the outside world by only one road and communication lines. But the most mysterious element of the stations was not their technical characteristics, but the mode of their operation and the tasks they performed in addition to the official detection of ballistic missiles. The construction of secret facilities deep in the Siberian Taiga required the creation of an entire infrastructure from scratch. The locations for the stations were selected based on several criteria: optimal geographical position for monitoring missile-threatening directions, the presence of hills for antenna placement, the possibility of covert construction, and remoteness from large population centers. As a result, construction took place in areas where previously there had only been hunting lodges and geological parties. In 1980, in the Krasnoyarsk region, near the city of Yeniseisk, construction began on a facility codenamed Ortu-OS-3 and call sign Yeniseisk 15. Formerly, it was a radio engineering facility, but local residents quickly realized that something related to defense was being built there. Columns of military trucks carried equipment under guard. The area was fenced off with multi-meter barbed wire fences, and checkpoints with armed guards were set up. Workers and specialists were recruited throughout the Soviet Union, offering high salaries and northern allowances. Many did not even know exactly what they were building. Information was given on a need-to-know basis, and everyone knew only their own area of work. At the same time, construction was underway in the Irkutsk region on an even larger facility near the village of Mishchelovka. designated Ortu Usolye Sibirskoye 7. This complex was intended to monitor the southeastern direction, possible missile launches from China, and American bases in the Pacific Ocean. Construction proceeded at a rapid pace, with work continuing around the clock in 3 shifts. In winter, with Siberian temperatures reaching -40 degrees, concrete work was impossible, so giant heated shelters were erected, under which foundations were poured and structures were erected. In summer, the main problem was swarms of mosquitoes and midges, from which people were saved only by special protective clothing and repellents. During the thaw, dirt roads turned into an impassable mess, and cargo deliveries were halted for weeks. Concrete roads were laid, and bridges were built across rivers and ravines to ensure year-round access. Power lines were stretched from distant hydroelectric power stations to the facilities. Poles, 30 to 40 meters high, carried high-voltage wires through the taiga for tens of kilometers. Clearing the right-of-way for the power lines was an epic undertaking in itself. It was necessary to cut down trees to create a path tens of meters wide, uproot stumps, and level the ground for the passage of equipment. At the same time, military towns were being built for the future staff of the stations and their families. 5-story residential buildings were constructed according to standard Soviet designs, along with schools, kindergartens, clinics, shops, and boiler rooms. These settlements were intended to provide a normal life for hundreds of families in conditions of complete isolation from the outside world. Communication with the mainland was maintained only through official channels and rare trips by special transport. A special regime of secrecy created an atmosphere of tension. Any departure from the territory required special permission, correspondence was subject to military censorship, and photography was strictly prohibited. Employees signed non-disclosure agreements and understood that any violation would have serious consequences, including criminal prosecution. Families lived in a state of uncertainty. They knew that their husbands and fathers were engaged in important government work, but they did not know the details. Children grew up understanding that their town was not marked on ordinary maps, and that they could not tell outsiders about where they lived. The station itself was built like a real fortress. Massive, reinforced concrete foundations went tens of meters deep to support the antenna structures weighing thousands of tons. The metal frames were assembled from special durable alloys that could withstand Siberian frosts and wind loads. The antenna arrays were assembled from thousands of individual elements, each of which required precise adjustment. An error of a few millimeters on one element could distort the directional pattern of the entire array. Tunnels and galleries were laid under the buildings for cables, cooling systems, and emergency passages. Autonomous life support systems were created in case the facility was isolated. The construction transformed the dense taiga into a high-tech military complex. But why such expense, such secrecy, such haste? The official version spoke of strengthening the country's defense capabilities, but some witnesses recalled strange details that did not fit into the usual picture of the construction of a military facility. In 1987, the construction of the Daryal U station near Yeniseisk became the subject of a serious international scandal that threatened the most important agreements between the USSR and the US. American reconnaissance satellites discovered the construction of a giant radar complex deep inside Soviet territory, and Washington accused Moscow of violating the anti-ballistic missile treaty signed in 1972. The essence of the accusation was that, according to the treaty, radar stations of the Missile Attack Warning System could only be located on the perimeter of state territory facing outwards. This restriction was introduced to prevent the creation of radar stations capable of tracking the trajectories of missiles after their launch and guiding anti-missiles towards them. A station on the perimeter can only see the launch itself and the initial part of the trajectory, while a station deep inside the territory can track the target throughout its entire flight. Yeniseisk was located more than 1,000 kilometers from the nearest border, which was a clear violation of the spirit of the treaty. The Soviet leadership found itself in a difficult situation. On the one hand, construction was well advanced, huge sums had been invested, and the facility was needed to close a gap in the missile defense system in the Northeast. On the other hand, a diplomatic scandal threatened the entire arms control system, which was a crucial element of stability during the Cold War. The Americans insisted on dismantling the station and even threatened to withdraw from the Missile Defense Treaty. Negotiations were conducted at the highest level. The Soviet side tried to prove that the station was intended solely for space surveillance and did not violate the treaty. Technical arguments were presented about the characteristics of the radar, its orientation, and its field of view. But American experts did not accept these arguments. They were well aware of the capabilities of the daryal station thanks to technical espionage and defectors. In 1987, the Soviet leadership made an unprecedented decision to suspend construction of the nearly completed station. This was a serious blow to prestige and defense capabilities. Thousands of people had worked for years in the most difficult conditions. Billions of rubles had been invested, and a unique infrastructure had been created. And all this was frozen in order to preserve the treaty. But the story did not end there. In 1989, a decision was made not just to mothball the facility, but to dismantle it completely. The station was about 95% complete. Antenna structures had been erected, equipment had been installed, and buildings had been completed. All that was needed was a few months of commissioning work, and the complex could have gone into combat duty. Instead, the reverse operation began, dismantling what had been built over many years. The equipment was dismantled, removed, and partially disposed of. Metal structures were cut up, concrete structures were demolished. Unique technologies and developments turned out to be unclaimed. Officially, this was explained by the desire to improve relations with the West and show goodwill in matters of disarmament. The USSR was entering a period of perestroika. Mikhail Gorbachev was pursuing a policy of new thinking and seeking mutual understanding with the American administration. The sacrifice of a multi-billion-dollar project was supposed to demonstrate the seriousness of Soviet intentions. But many military personnel and scientists perceived this decision as a betrayal of national interests. They saw how the U.S. was actively modernizing its missile defense systems and developing new types of weapons, while the USSR unilaterally abandoned its existing means of defense. There were rumors that the decision to dismantle the station was made under pressure not only from American diplomacy, but also from some behind-the-scenes negotiations at the highest level. Some conspiracy theorists claimed that the station was sacrificed as part of a broader deal to reduce strategic weapons. Others said that the Americans had compromising information about the station's technical problems or about some secret experiments that were being conducted there. The facility's staff, who had worked for years in extremely difficult conditions, were shocked. Many were transferred to other facilities, and their families were forced to move. The military town began to empty. Some buildings were handed over to local authorities, while others were abandoned. The station's territory was cleared, leaving only concrete bases and foundations. Now, only ruins overgrown with taiga remain at the site of the once secret complex. Local residents say that it is a strange place, that inexplicable phenomena occur there, and that equipment sometimes fails for no apparent reason. What exactly happened there during the years of construction, and what the archives hide, remains a mystery. The story of the dismantling of the Yenisei station is not the only mysterious page in the history of the Soviet radar giants. The decision to destroy a nearly completed facility worth billions of rubles remains one of the most controversial in the history of the Soviet defense program. By the time construction was halted in 1987, the station was approximately 95% complete. All the main structures had been erected. The transmitting and receiving antennas had been installed. The computing complex had been set up. The buildings had been constructed, and the infrastructure had been created. All that remained was commissioning and testing, a stage that usually takes several months. The complex could have been put on combat duty as early as 1988 or 1989. Instead, work was frozen, personnel were withdrawn, and the facility was mothballed. 2 years later, an even stranger decision was made, not just to keep the station mothballed in case work might resume, but to completely dismantle it. A process began that could be called the destruction of our own heritage. Special teams dismantled equipment that had taken years to install and configure. Electronic units, each of which had been manufactured in single copies by specialized enterprises, were removed and taken away. Some of the equipment was attempted to be repurposed for other facilities, but much of it was unique and unsuitable for other purposes. Antenna structures, thousands of tons of special metal, precisely machined and assembled, were cut up for scrap. Concrete structures were blown up. Kilometers of underground cables were dismantled. Even roads and power lines were partially dismantled. The dismantling operation cost hundreds of millions of rubles, additional expenses on top of the billions already spent. Why was such total destruction necessary? The official version is that it was necessary to fulfill international obligations and demonstrate peacefulness. But this version raises questions. The ABM Treaty only required the cessation of construction of the radar station in an unacceptable location, but not necessarily its physical destruction. A mothballed facility would not have violated the treaty and could have been activated if the situation changed. Moreover, by the early 1990s, it had become clear that the USSR was on the verge of collapse, and defense issues were becoming critical. There is a version that the dismantling was a condition of some secret agreements between the Soviet and American leadership. According to some sources, the American side insisted on the physical destruction of the facility and even offered financial compensation for its dismantling. Allegedly, the U.S. feared that in the event of political changes in the USSR, the new leadership could quickly complete the station and gain an advantage in early warning systems. Another version is related to technical reasons. There is a view that during construction, serious flaws or errors in the design were discovered that made it impossible for the station to function normally. Perhaps there were problems with the computing complex, which could not cope with processing data from a huge phased array, or with interference protection. The station could be blinded by its own side pedals or by natural radio interference. But if there were technical problems, why didn't they try to solve them? Soviet defense science had repeatedly proven its ability to overcome the most complex technical challenges. The third, conspiracy theory version states that the station was used not only to detect missiles, but also for some experiments related to the effect of powerful radio emissions on the atmosphere, ionosphere, or even the human psyche. There are theories that super-powerful radars could have been used to create local disturbances in the ionosphere that would affect the propagation of enemy radio waves or even the weather. Allegedly, these experiments yielded unexpected results, which were decided to be classified, and the station was destroyed along with all traces of the research. The facility's personnel involved in the dismantling signed additional non-disclosure agreements. Many of them still refuse to give interviews or speak in extremely vague terms. The archives on this facility are still partially classified, even though more than 30 years have passed. What is hidden in these documents? While the Yenisei station was dismantled under pressure from international obligations, the fate of the second Siberian facility, the station near the village of Mishchelovka in the Irkutsk region, proved even more mysterious. This complex, designated Ortu Usolye Sibirskoye 7, was supposed to monitor the southeastern direction and close gaps in the radar field of the missile attack warning system from China and American bases in the Pacific Ocean. Construction began in the early 1980s and progressed rapidly, despite the difficulties of the Siberian climate and the remoteness from industrial centers. By the end of the 1980s, the station was about 70–80% complete. The main buildings had been erected, the foundations for the antennas had been laid, communications had been installed, and a military town had been built. All that remained was to install the antenna systems and electronic equipment, work that would take several more years. But the collapse of the Soviet Union in 1991 and the ensuing economic crisis put an end to the project. Funding was cut off, personnel were withdrawn, and the facility was frozen. The unfinished station became a monument to the unfulfilled plans of the Cold War. It would seem that this was the end of the story. But in the mid-1990s, there was an unexpected turn of events. According to some sources, the American side offered the Russian government assistance in completing the station's construction through diplomatic channels. This proposal seemed absurd. Why would the U.S. help a potential adversary complete a missile defense system facility? The official explanation was that the station could be used to monitor space debris and control outer space as part of international cooperation. In the 1990s, the issue of space debris did indeed become relevant. Thousands of satellite and rocket fragments had accumulated in orbit, posing a danger to operational spacecraft. A powerful radar could track even small fragments and warn of collision threats. It sounded reasonable, but questions arose. Why didn't the Americans propose building a specialized space monitoring station from scratch, namely, completing the military facility of the SPRN system? What guarantees could there be that Russia would not use the station for its intended purpose, to detect ballistic missiles? And most importantly, what interest did the U.S. have in investing money in Russian defense infrastructure? There is a theory that the proposal was part of a more complex scheme. Allegedly, the American side wanted to gain access to Soviet phased array antenna technology, which in some respects surpassed its Western counterparts. Participating in the completion of construction under the pretext of civilian use would have allowed them to study the design from the inside, obtain technical documentation, and understand how it worked. In return, Russia would have received a ready-made station and funding for its operation, a lucrative deal for an impoverished country. Another version links the proposal to the U.S.'s desire to control the capabilities of the Russian missile defense system. If the station is built with their participation, they will know its parameters and limitations and may even be able to build in elements that allow them to monitor its operation or even influence it at a critical moment. This would be a classic technical espionage operation under the guise of cooperation. There were even more exotic rumors. Allegedly, American specialists were interested not so much in the technology of the station itself, but in some additional systems that were installed there or planned to be installed. There was talk of some experimental installations for studying the effects of powerful radio emissions on the Earth's ionosphere and magnetosphere. Some conspiracy theorists linked this to the HARPY program, an American project to study the ionosphere in Alaska, around which there are many conspiracy theories. The Russian government ultimately rejected the American proposal. Officially, this was explained by the lack of need for another space monitoring station, as other means were available for this purpose. Unofficially, various reasons were cited, ranging from unwillingness to allow foreigners access to a secret facility to suspicions about the true intentions behind the proposal. The station remained unfinished. Over the course of several years, it was gradually looted by local residents and scrap metal collectors. Non-ferrous metals, cables, equipment, anything of value was taken away and sold for scrap. Buildings were destroyed, structures collapsed, and the area became overgrown with weeds. Now it is a typical abandoned site in the post-Soviet space. Ruins in the Taiga, reminiscent of former ambitious plans. But local residents say that sometimes people in civilian clothes come to the site, take measurements, take photographs, and make notes. Who they are and what they are looking for among the ruins is unknown. What exactly the Americans wanted to find or learn at this station remains a mystery. The history of the Soviet daryal stations includes not only lengthy construction and mysterious dismantling, but also dramatic episodes of physical destruction of completed facilities. The station in Skrunda, Latvia, operated from 1971, monitoring the western direction and providing early warning of a possible missile strike from the Atlantic and Western Europe. After the collapse of the USSR, it found itself on the territory of independent Latvia, which created a very difficult geopolitical situation. Russia insisted on continuing to operate the station as an important element of its missile attack warning system. The Latvian authorities demanded the withdrawal of Russian troops and the dismantling of the facility. The station became a bargaining chip in negotiations on the withdrawal of Russian troops from the Baltic states, a symbol of post-Soviet confrontation. Discussions continued for several years, and the station continued to operate under Russian personnel, but its fate was sealed. In 1998, Russia agreed to dismantle the station in exchange for certain concessions on other issues. The operation to dismantle the complex, which had been built over decades and cost billions of rubles, began. But dismantling is too mild a word for what happened. The American company Controlled Demolition Incorporated, specialists in blasting and demolition of complex structures, was brought in to assist with the process. This same company would later become infamous in connection with the events of September 11, 2001, and the conspiracy theories surrounding them. The choice of an American company to destroy Soviet military infrastructure seemed symbolic, to say the least. In the summer of 1998, a series of powerful explosions shook the vicinity of Skrunda. The 17-meter concrete walls of the radar center's buildings, capable of withstanding a close nuclear blast, were reduced to rubble. A giant antenna, as tall as a 20-story building, slowly tilted and crashed to the ground with a roar, raising clouds of dust. Local residents watched the destruction of a facility that had been part of their lives for decades, a source of employment and the reason for the region's special status. But Skrunda was not the only victim. In Kazakhstan, near the city of Sari-Shagan, there was another station, Daryal, which monitored the southern direction. After the collapse of the USSR, it remained on the territory of independent Kazakhstan. The fate of this facility turned out to be similar to that of the Latvian one. Demands for liquidation, lengthy negotiations, and ultimately dismantling. But while Skrunda was destroyed by explosions, the Kazakh station was partially dismantled and partially simply abandoned to looting. Equipment was removed, metal structures were cut up, and buildings were demolished. By the early 2000s, only concrete ruins remained of the once powerful complex. The participation of an American company in the dismantling of Soviet military facilities gave rise to many conspiracy theories. Why did the U.S. need to personally participate in the destruction of the stations? The official explanation was to control the dismantling process within the framework of international disarmament agreements. But critics pointed out that such control could have been exercised by international observers without direct participation in the work. There is a version that the real goal was to study the construction of the stations from the inside during the dismantling process. Controlled demolition specialists gained access to all elements of the complex, were able to study the technology in detail, photograph and document everything. Information about Soviet phased array antennas, computing systems, and interference protection principles was of enormous intelligence value. The dismantling was the perfect excuse for technical espionage under the guise of legitimate activity. Another version is related to the destruction of evidence. Allegedly, in addition to the main SPRN system equipment, these stations also housed some experimental installations, information about which was not supposed to fall into the hands of third countries or international inspectors. Thorough cleaning of the territory by American specialists ensured that no compromising materials remained. Another theory concerns radioactive contamination. There were rumors that the station's computing complexes used some kind of radioisotope power sources, or that the territory was contaminated as a result of accidents or tests. The participation of a Western company in the cleanup may have been a condition for the transfer of the territory to national governments. Station personnel, Russian military and civilian specialists watched with bitterness as the facilities to which they had devoted years of service were destroyed. Many were convinced that the dismantling was a strategic mistake that left Russia without key elements of its early warning system. The events of the following years proved these fears to be justified. Gaps in the radar field had to be hastily filled by building new stations. But why was it impossible to preserve the existing ones? Of all the stations in the daryal family, only one survived the storms of the 1990s and continues to operate to this day, the complex near the city of Pechora in the Komi Republic. This station, commissioned in 1984, monitors the northern direction, possible ballistic missile launches across the North Pole from North America. Its uniqueness lies in the fact that it has not only survived, but has also undergone extensive modernization, remaining a key element of Russia's missile attack warning system. After the collapse of the USSR, the station remained on Russian territory and avoided the geopolitical conflicts that destroyed its sisters in Latvia and Kazakhstan. But simply surviving was not enough. The equipment from the 1980s was becoming obsolete. The electronic base needed to be replaced, and the computing power did not meet modern requirements. By the end of the 1990s, the question arose: either close the station or carry out a radical modernization. The second option was chosen. In the early 2000s, a unique operation began at the Pechora station, replacing all the electronic components while preserving the basic structures. The antenna systems, foundations, and buildings remained the same, but all the signal processing equipment, computing complexes, and control systems were replaced with modern ones. It was a kind of Theseus's ship, a philosophical paradox where all the parts are gradually replaced, but the object remains the same. The peculiarity of the modernization was that it was carried out without interrupting combat duty. The station could not be shut down. This would have created a breach in the warning system. Therefore, the equipment was replaced in sections. One part continued to operate on the old equipment, while the other was already being transferred to the new. This required the precision work of engineers to ensure the compatibility of different generations of systems. New computing complexes based on modern multiprocessor systems increased productivity hundreds of times over. Improved signal processing algorithms made it possible to increase the accuracy of target parameter determination and interference immunity. Digital processing replaced analog processing, which made it possible to flexibly adjust the characteristics to changing conditions. By the end of the 2000s, the modernization was complete, and the station was given the index daryal modernized. In fact, it was a new radar in an old shell. The Pechora station became the only functioning monument to the Soviet radar school, a bridge between eras. Its 40-meter transmitting antenna and 100-meter receiving array, erected in the 1980s, continue to carry out combat duty in the 2020s. The station's personnel, servicemen of the Russian Space Forces, work in a state of constant readiness. The operator room displays the radar situation in the sector of responsibility on its screens. Every missile launch, every spacecraft passing through the viewing area is recorded and analyzed. The information is transmitted in real time to the central command post of the Missile Attack Warning System in Moscow. But the Pechora station keeps more than just technical secrets. Military personnel who have served there over the years sometimes talk about strange occurrences, about unexplained signals that did not correspond to ballistic missiles, spacecraft, or meteors, about periods when the system recorded anomalies in the ionosphere above certain areas. They talk about operating modes that are not mentioned in open sources. Officially, the station is only involved in detecting ballistic missiles and space objects. But the power of radiation in the hundreds of megawatts, the ability to influence the ionosphere, and the presence of specialized computing complexes all open up opportunities for experiments that are not disclosed. Are there operating modes at the station related to the study, or even modification of ionospheric processes? Can powerful radio emissions be used not only to receive reflected signals, but also to actively influence the atmosphere? These questions belong to the realm of conspiracy theory, but the principles of physics allow for such possibilities. Pechora remains an active secret base. Despite the declassification of general information about the SPRN system, the details of the station's operation, equipment characteristics, and operating modes remain classified. Journalists are not allowed in, photography is prohibited, and the area around the station is controlled. Only authorized specialists know what exactly is happening behind the barbed wire fences. Why did only one of all the daryals survive? And what role does it play in Russia's modern defense system? While the old daryal stations were being modernized or destroyed, a new generation of long-range radar systems was being developed in Russia. By the end of the 1990s, it became clear that it was impossible to restore the lost daryal stations. They were too expensive, took too long to build, and many of the technological chains involved in their production had been destroyed, along with the collapse of the USSR. A new approach was needed, a new technology that would be cheaper, faster to build, and more technologically advanced in operation. This is how the Voronezh project was born, a revolutionary family of radar stations that was supposed to fill the gaps in Russia's radar field. Voronezh stations use a fundamentally different architecture compared to daryal. Instead of separate transmitting and receiving positions, a single phased array antenna is used, which works for both transmission and reception. This simplifies the design and reduces costs. Instead of monolithic reinforced concrete buildings several dozen meters high, there are compact modular structures that can be erected faster and cheaper. The computing base is fully digital, built on modern processors, which provides a huge gain in performance with lower energy consumption. One of the first facilities of the new generation was the Voronezh DM radar station near Yeniseisk, in the Krasnoyarsk territory, where the daryal was built and then dismantled in the 1980s. Construction began in 2005 and was completed in 2009, a total of 4 years compared to the decades required for daryal. The facility went on combat duty and began monitoring the northeast direction. In October 2016, a significant event took place. The Yenisei station detected a target launched from North America for the first time. It was a test launch of an American ballistic missile from Vandenberg Air Force Base in California. The station recorded the launch, tracked the trajectory in the initial phase, and transmitted the data to the control center. The event confirmed that the new generation of radar stations was fully functional and capable of performing combat tasks. The Voronezh stations have a target detection range of up to 6,000 kilometers, comparable to that of the daryal. They can simultaneously track up to 500 objects, which significantly exceeds the capabilities of their predecessors. The accuracy of determining coordinates and trajectory parameters has been improved thanks to advanced processing algorithms. Interference immunity has been increased through adaptive filtering and the use of complex signals. Voronezh surpasses daryal in all key parameters, while being significantly cheaper. But there is one but. Voronezh stations operate in a shorter wavelength range, decimeter instead of meter for daryal. This provides advantages in accuracy and resolution, but also creates limitations. Shorter waves are more dependent on the state of the ionosphere and pass less easily through plasma and ionized areas. In conditions of strong geomagnetic disturbances, or when the enemy uses means of influencing the ionosphere, efficiency may decrease. In addition, The decimeter range is less suitable for over-the-horizon propagation in certain modes. The Yenisei station became the flagship of the new system, but not the only one. A network of Voronezh stations of various modifications has been deployed around the entire perimeter of Russia. Voronezh M operates in the meter band, like the old daryal, Voronezh DM in the decimeter band, and Voronezh SM in hybrid mode. Each station monitors its own sector, and their fields of view overlap, creating a continuous radar field around the country. The construction technology has been perfected to the point where it is now a conveyor belt process. It takes 3 to 4 years from the start of work to commissioning. This has allowed Russia to rebuild its missile attack warning system, which was destroyed in the 1990s, in 15 years. But the strange synchronicity of events raises questions. 2 decades after daryal was dismantled due to an international scandal, a new station performing the same function is being built on the same site. Formally, this does not violate the ABM Treaty, because the treaty itself was denounced by the US in 2002. But it looks as if everything was planned in advance. Sacrifice the old station to improve relations, buy time, develop new technology, and return to the same place with a more advanced system. Is this a coincidence or a long-term strategy? The Yenisei Taiga holds the answers to many questions, but is reluctant to reveal them. The technological progress embodied in the Voronezh stations can only be appreciated by understanding how far radar technology has advanced in the 3 decades since the creation of the Daryalovs. The phased array antenna of a modern radar contains several thousand active modules, each of which is a miniature transceiver with its own amplifier, phase shifter, and control electronics. These modules work synchronously, forming a beam of a given shape and direction in a purely electronic way, without any mechanical movements. The beam switches from one target to another in microseconds, allowing resources to be redistributed almost instantly between scanning the space and tracking detected objects. The Voronezh station's computing complex performs hundreds of billions of operations per second, a level of performance that was unthinkable at the time of daryal's creation. Radar data is processed in real time using sophisticated algorithms for noise filtering, target detection against interference, and object type recognition. The system is capable of distinguishing a ballistic missile warhead from a false target, meteorite, or space debris based on the nature of the radar reflection and movement characteristics. Machine learning algorithms allow the station to adapt to new types of targets and interference, constantly improving its performance. The operating mode is automatically optimized depending on the situation. In a calm situation, the station operates in survey mode, scanning the entire sector of responsibility at regular intervals. When a target is detected, part of the resources are switched to tracking it. The beam is focused on the object, and the irradiation frequency is increased to accurately determine the trajectory. If a massive launch is detected, the mode changes to priority tracking of threatening targets. All this happens automatically, without operator intervention, in a fraction of a second. The energy efficiency of the new stations is an order of magnitude higher than that of the Daryalov stations. Solid-state amplifiers based on modern semiconductor technologies have replaced tube transmitters, reducing power consumption and increasing reliability. The cooling system has become more compact. Maintenance has been simplified thanks to the modular design. A failed module is simply replaced with a new one, without the need for on-site repairs. The station's availability factor, the proportion of time it is operational, is approaching 99%. But the most revolutionary change has been in the software. The station runs on a specialized real-time operating system that ensures guaranteed response times to events. The application software includes modules for signal processing, antenna control, target designation, interaction with the command post, and diagnostics. The total volume of program code is millions of lines written in compliance with strict security and reliability standards. Software updates can be performed remotely, allowing for rapid implementation of improvements and fixes. This makes the station not a static structure, but an evolving system whose capabilities grow over time. The station's connection to the central command post of the missile attack warning system is organized via secure fiber optic and satellite channels with multiple redundancy. Data is transmitted in encrypted form in real time. The time from target detection to reporting to the command center is a matter of seconds. This is critically important, as only a few minutes are available to make a decision on how to respond to a missile attack. However, behind all these impressive technical characteristics lies the question: are these powerful systems used only for missile detection? The megawatt-level power output, the ability to focus energy into a narrow beam, and the ability to operate in different modes all open up potential for applications that are not publicly discussed. It is known that powerful radars can affect the ionosphere, creating local inhomogeneities that affect the propagation of radio waves. This can be used to suppress enemy radio communications or to improve the performance of one's own communication systems. There are theoretical studies on the possibility of using focused radio waves to affect the electronics of missiles and aircraft at long distances. There are persistent rumors that some modes of operation of the stations are strictly classified and are not related to target detection. The extent to which these rumors correspond to reality remains a closely guarded secret. But the technical capabilities for such applications certainly exist. For decades, an aura of mystery has surrounded Siberian radar stations, giving rise to legends passed down from locals to visitors, from old officers to young ones. Some stories sound like typical army tales, while others make you wonder if there is something real behind them. Residents of villages located near the stations talk about periods when strange light phenomena appear over the taiga. The descriptions vary. Some talk about an unusual color, northern lights appearing not in the northern part of the sky, but directly above the station. Some have seen pulsating lights in the ionosphere, synchronized with the radar. Some claim that during station tests, the night sky was lit up by flashes, although there were no visible light sources at the facility. The scientific explanation for these phenomena links them to the ionization of the air by powerful radio waves. But some witnesses insist that they saw something that does not fit within the framework of known physics. There are stories about the impact of the stations on technology. They say that within a radius of several kilometers from an operating radar station, electronic devices can malfunction. Cars stall, radios pick up only noise, compasses show the wrong direction, and GPS navigators lose their signal. Hunters avoid approaching the stations because the equipment doesn't work there. It is officially recognized that powerful radars do indeed create strong electromagnetic fields that can affect sensitive electronics, but the areas of influence are strictly calculated and controlled. Nevertheless, Stories of unexplained equipment failures at great distances from the stations continue to emerge. There are legends about the impact on people. Some station workers complained of unexplained ailments, headaches, and sleep disturbances. Official medicine attributed this to stress, shift work, and the harsh climate. But stories persistently surfaced that certain station operating modes caused strange sensations in the staff. Unreasonable anxiety, disorientation, and auditory hallucinations. Of course, such effects could be the result of exposure to infrasound from operating equipment or psychological pressure from working at a secret facility. Or perhaps powerful radio emissions are indeed capable of influencing bioelectrical processes in the brain? This question remains a matter of speculation. One of the most persistent legends is related to the discovery of unidentified objects. Allegedly, station operators repeatedly recorded targets that did not behave like ballistic missiles, satellites, or aircraft. The objects appeared on the screens suddenly, moved at impossible speeds, changed direction at right angles, and disappeared without a trace. Reports were written, investigations were conducted, but no official conclusions were published. Skeptics explain such cases as data processing errors, atmospheric anomalies, or interference. Those who believe in UFOs see this as proof of visits to Earth by extraterrestrial intelligence interested in military facilities. A rational version suggests that these could have been tests of secret hypersonic aircraft, information about which is classified even for radar station personnel. There are stories about times when the station was visited by special groups in civilian clothes, without any distinguishing marks. They conducted experiments that were not reported through the usual official channels. The equipment operated in non-standard modes. Personnel were removed from certain rooms, and after the visitors' visits, orders were given not to discuss what was happening even among themselves. What kind of experiments were these? Testing of secret operating modes? Research into the impact on the ionosphere? Testing electronic warfare equipment? Or something else that is still taboo to talk about even decades later? Local residents tell stories of strange finds in the taiga around the stations. Some people stumbled upon metal debris of unknown origin, unlike ordinary trash or technical parts. Others have found areas of forest where the trees grew deformed, with twisted trunks, even though the surrounding forest was normal. There have been various explanations for this, ranging from waste disposal to geomagnetic anomalies and radiation exposure. No scientific research has been conducted in these areas, or the results have not been published. Of course, most of these stories may be the product of imagination, misinterpretation of normal phenomena, or a desire to add romance to a boring job or life in a remote village. Secrecy always gives rise to speculation. But there remains a persistent feeling that there is a grain of truth behind some of the legends, that certain events did indeed take place, but that information about them is being carefully concealed. What did people actually see in the Siberian taiga in those years when the stations were operating at full capacity and when there was no strict public control over them? Despite the partial declassification of information about the missile attack warning system and the appearance of publications about the Daryal and Voronezh stations, a significant portion of the data remains classified as top secret or of special importance. Even now, in the 2020s, when the Cold War has long since ended, access to the archives is strictly limited, and attempts by journalists or researchers to obtain detailed information are met with a wall of silence. What is the remaining 10% of the 90% declassified documents silent about? First of all, the exact technical characteristics of the stations remain secret. General parameters are published. Detection range up to 6,000 kilometers. The number of simultaneously tracked targets several hundred. But specific figures, operating algorithms, and interference protection features are all classified. The reason is clear. The enemy must not know how to bypass the detection system, at what altitudes or trajectories objects can remain undetected, or what types of jamming are effective. But the question arises, why is information about stations that have already been destroyed classified? What security threat could information about Daryal, which was blown up in Latvia 27 years ago, pose? Perhaps these technologies are still relevant and are used in modern systems. Or perhaps there is something more to it. Information about the operating modes of stations not related to the detection of ballistic missiles is strictly classified. Officially, the radars are intended only for the early warning system, but technically, they are capable of performing other tasks. It is known that the stations are used to monitor outer space, track satellites, and space debris. But can they be used to suppress enemy radio-electronic systems, to jam missile guidance systems, to influence the ionosphere in order to improve or worsen radio wave propagation conditions? These questions hang in the air without answers. The details of incidents and emergencies are classified. Over decades of operation, there have certainly been accidents, equipment failures, and operator errors. Have there been false alarms when the system mistook meteorological phenomena or technical interference for a missile attack? How close did the world come to disaster due to automation errors or human factors? There is a well-known case from 1983 when Stanislav Petrov, an officer in the Soviet early warning system, prevented a nuclear war by recognizing a false alarm. But how many other cases were there that were not reported? Archives related to unusual detections are of particular interest. According to the testimony of former military personnel, for decades, stations recorded objects that could not be classified. Each such case had to be accompanied by a report, an investigation, and a conclusion. Where are these documents? Why haven't they been declassified, even though decades have passed? The skeptical explanation: because there is nothing interesting there, only technical interference and equipment errors. The conspiracy theory: because there is information there that they don't want to make public, either about visits by unidentified objects or about their own secret aircraft. There is a theory that some stations were used to conduct experiments unrelated to their main function. We are talking about possible research into the effects of powerful electromagnetic fields on biological objects, the human psyche, and atmospheric processes. The power of radiation in the hundreds of megawatts and the ability to focus energy in a specific area of space is a tool not only for radar, but also for experimental atmospheric physics. Were such experiments conducted? If so, what results were obtained? This information could relate to the development of new types of weapons, electronic warfare systems, climate weapons, means of influencing the human psyche through electromagnetic fields. All this sounds like science fiction, but the physical principles of such effects are known, and a powerful radar can theoretically be used as an experimental facility. Documents on cooperation with foreign intelligence services remain classified. It is known that American intelligence was actively interested in Soviet radar stations, tried to obtain technical information, and planted agents at the facilities. There are known cases of betrayal and the transfer of secrets. But the full picture of espionage operations around the stations has not been revealed. Who passed on what information and when? What countermeasures were taken? Were there cases of disinformation, when false data was deliberately leaked to mislead the enemy? Finally, the true reason for the decision to dismantle the almost completed stations in Yeniseisk and Irkutsk remains a mystery. The official versions, diplomatic pressure and lack of funding, seem insufficient to explain the destruction of multi-billion-dollar facilities. Archives of high-level negotiations, records of closed meetings of the Politburo and the Security Council of those years could shed light on the real motives. But these documents are either classified, destroyed, or held in private archives that are inaccessible to researchers. What is hidden in the remaining 10% of information about the Siberian radar giants that remains secret? While the old stations are becoming history, modern Russia is actively developing a new generation of radar systems, creating a continuous radar field around the entire perimeter of the country. By 2025, a network of Voronezh stations will be formed, providing control of all strategically important directions, from Kaliningrad in the west to Primorye in the east, from Murmansk in the north to Crimea in the south. Each station monitors a sector several thousand kilometers wide, and their coverage areas overlap, leaving no dead zones. This means that the launch of a ballistic missile from any point of possible confrontation will be detected within a minute after launch. The Yenisei station in the Krasnoyarsk region monitors the northeast direction, potential launches from Alaska and the west coast of the United States. The station in Letusi, near St. Petersburg, looks west and northwest, tracking the Atlantic direction and submarine bases in the North Atlantic. The facility in Armavir in southern Russia monitors the southern direction, the Mediterranean, the Middle East, and the Indian Ocean. The station in Orsk in the Urals covers the southeast sector. The Pechora daryal continues to stand watch in the northern direction. There are plans to build additional stations to complete the circuit. The technology is constantly evolving. The latest modifications to Voronezh SM combine the advantages of the meter and decimeter ranges operating in hybrid mode. This allows them to adapt to different radio wave propagation conditions and ionosphere states. Artificial intelligence algorithms are being introduced for automatic target type recognition, trajectory prediction, and anomaly detection. The performance of computing complexes doubles every few years thanks to the use of the latest processors. Interference immunity is increased through the use of ultra-wideband signals and adaptive processing methods. The system is becoming not just a network of individual stations, but a unified radar complex with centralized control. Data from all stations flows to the main command center in Moscow, where supercomputers form a comprehensive picture of the radar situation in real time. If one station detects a target, the information is immediately transmitted to neighboring stations, which direct their beams to confirm the detection and refine the parameters. Such cooperation greatly increases the accuracy and reliability of the system. The time from the detection of a ballistic missile launch to the report to the highest military and political leadership is less than a minute. Automatic systems analyze the trajectory, determine the probable target, and calculate the time to impact. A human operator controls the process, but the main work is done by computers. The speed of events is such that human reaction is too slow. This creates new risks. What if the system fails? What if the algorithm misinterprets the data? Protection against such situations includes multi-level verification, duplication by various means, and the final decision remains with humans. But the line between automation and human control is becoming increasingly blurred. The Russian SPRN system is integrated with international missile launch control systems. There are agreements with the US on mutual notification of ballistic missile launches, and hotlines are in place to prevent errors and misunderstandings. Data from Russian radars is used by international organizations to monitor outer space and warn of dangerous satellite collisions. These are elements of trust in an era when relations between powers are far from smooth. But behind the facade of cooperation, the technological race continues. Russia is improving its radars, the US is developing missile defense, and China is building its own early warning system. New types of threats are emerging. Hypersonic gliding vehicles that do not fly along a ballistic trajectory and are more difficult to detect. Microsatellites capable of performing the functions of space strike systems are swarming in orbit. Electronic warfare capabilities capable of jamming radars are being developed. Detection technologies must constantly evolve to stay ahead of countermeasures. The Siberian Taiga remains the most important battleground in this invisible war of technologies. Here, among the uninhabited spaces, far from prying eyes, the latest developments are being tested. Here, modes of operation are being worked out, which are then replicated at other stations. Here, research is likely being conducted, the results of which will only become known decades later, when the archives are declassified. The future of radar is linked to the transition to even higher frequencies, the use of quantum technologies for signal processing, and the creation of distributed systems consisting of many small stations instead of a few giant ones. Perhaps the next generation of radars will be located in space, on satellites, forming an orbital radar field. Technologies that seemed like science fiction when the first daryals were created are becoming a reality. But the main thing remains unchanged: confrontation, mutual restraint, and the balance of fear of catastrophe. Radar stations are not just technical structures. They are symbols of an era when humanity gained the ability to destroy itself in 30 minutes. And the only thing that keeps it from pressing the button is the knowledge that the other side will press its button in response. Missile attack warning systems are the technological embodiment of the doctrine of mutually assured destruction. They must work flawlessly because a mistake could cost billions of lives. And they must remain secret because knowledge of their weaknesses tempts the enemy to launch a disarming strike. In this paradox exist the Siberian radar giants, open to the world and at the same time hidden behind a veil of secrecy, protecting the world and being part of the system of its possible destruction.